The RLC Parallel Circuit. A resistor, an inductor, and a capacitor are connected in parallel to an AC source with voltage amplitude V and angular frequency omega. Let the source voltage be given by V is equal to capital V cosine omega t. Part A. Show that each of the instantaneous voltages V sub R, V sub L, and V sub C at any instant is equal to V, and that I is equal to I sub R plus I sub L plus I sub C, where I is the current through the source, and I sub R, I sub L, and I sub C are the currents through the resistor, inductor, and capacitor, respectively. Okay, so we have a resistor, inductor, and capacitor connected in parallel to an AC source. Voltage, instantaneous voltage, capital V cosine omega t. You can see that we have these A, B, and C are at the same potential. D, E, and F are at the same potential. So these are equipotential points. So we can see that since A, B, and C are equipotential points, and D, E, and F are also equipotential points. That's the meaning of parallel connection. The voltage across the resistor, so this would be plus minus V sub R, voltage across the inductor plus minus V sub L, voltage across the capacitor plus minus V sub C. These three voltages should be equal. So we see that V sub R is equal to V sub AD. That's the voltage difference between AD, which is equal to V sub L. That's the voltage difference between BE, and that's equal to the voltage across the capacitor, which is the voltage across CF. So because these are all equipotential points, A, B, C, and D, E, F are equipotential points, so the voltage between A and D is equal to the voltage between B and E, and is equal to the voltage between C and F, which is VR equals VL equals VC. Now, looking at the current that flows through the source here, I, we can see that at this junction, this current spreads into two. So there is I sub R, the current flowing through the resistor. And here it spreads into two again. So there's I sub L and there's I sub C. So writing Kirchhoff current law at junction B. So if I write Kirchhoff current law at junction A, let's start with A, I see that the incoming current I is equal to I sub R plus I prime, where I prime is this current here. And writing Kirchhoff current law at junction B, I see that I prime is equal to the current entering the junction is equal to the two currents leaving the junction, IL plus IC. So combining these two, I obtain I is equal to I sub R plus I sub L plus I sub C. So that's the end result. It's just an application of Kirchhoff current law. So we were supposed to show that the instantaneous voltages are the same and the currents add up to the current through the source. Okay. Let's move on to part B of the problem. What are the phases of I sub R, I sub L, and I sub C with respect to V? Use current phasors to represent I sub R, I sub L, and I sub C. In a phasor diagram, show the phases of these four currents with respect to V. Okay, so Let's do that here. First of all, the voltage across the resistor V is equal to I sub R times R. So I can see that I sub R, the current through the resistor, is the voltage V divided by the resistance R, which means this current is in phase with V. On the other hand, this voltage V is equal to L d I sub L dt. It's the voltage across the inductor. So I can see that I sub L is integral of V, capital V cosine omega t over L dt. And this integral gives me capital V over omega L sine omega t. All right. And what is the relationship between sine omega t and cosine omega t? I can see that here I sub L is equal to capital V over omega L, inductive reactance, cosine omega t minus pi over 2. So if you use the trigonometric identity, this is cosine A minus cosine B, cosine A cosine B, so it's cosine omega t cosine pi over 2, which is 0, plus sine A sine B, which is sine omega t sine pi over 2. So this is indeed sine omega t. So therefore, the phase relationship is minus pi over 2. On the other hand, if I look at the current through the capacitor I sub C, that is equal to capacitance dV dt, dVc dt, but Vc is the voltage V. So that's going to be minus omega C capital V sine omega t. So I'm taking the derivative of cosine. I get minus omega sine omega t. And that can be written in terms of cosine as well. I sub c is capital V omega c cosine omega t plus pi over 2. So the current through the capacitor leads the voltage by pi over 2. Okay, so I have found the phase relationship. No phase difference for the IR. There is a lagging by pi over 2 for the inductor and leading by pi over 2 for the capacitor. If I represent this in a phasor diagram, I have at time t, omega t angle with respect to the x-axis, the current I sub r phasor is capital V over R cosine omega t, and at the same time I have for this voltage V, let's pick this color here. Okay, so this is V the voltage phasor V, that is capital V cosine omega t. And then I have the inductor current. So let's look at inductor current. I sub L phasor, that is capital V divided by omega L cosine omega t minus pi over 2. So because it's minus, I have to go in the clockwise direction. And as for the current through the capacitor, this phasor is I sub c is equal to v omega c cosine omega t plus pi over 2. So that's how I can represent all of these currents and their phase relationship on a phasor diagram in reference to the AC source voltage capital V cosine omega t. Let's move on to part C of the problem. Use the phasor diagram of part B to show that the current amplitude for the current I through the source is square root of IR squared plus IC minus IL parentheses squared. Okay, so you can see that this IC and IL, they're opposing each other. So the current basically that has the net positive direction is IC phasor minus IL phasor. But at the same time, so I have carried this one up here. So IC minus IL is this vector. And there's a 90-degree with respect to I sub r. So I'm going to have the I sub r phasor here. And these three phasors will add up to give me the current phasor, the total current phasor. Basically, this equation that I have here is actually a phasor equation. So this is these phasors adding up to give me the current phasor. Okay, so the magnitude of the current amplitude is the magnitude of the I phasor, which is IR square plus IC minus IL parentheses square root. That's because of this right triangle here. So I have one side magnitude of I sub r phasor. On the other side, I have magnitude of IC minus IL phasor. So this gives me the hypotenuse magnitude of the current phasor, which is I. So with that, I is equal to I sub r square plus I sub c minus I sub l square let's do this with the parentheses, I sub c minus I sub l parentheses squared square root. That's the answer I was looking for. Now, I want to note here that I have resistive reactance R. The voltage amplitude V is equal to I times R. The inductive reactance is omega L, which means the voltage amplitude is equal to IL omega L. And at the same time, the capacitive reactance is 1 over omega C, which means the voltage amplitude is IC divided by omega C. So I have this relationship between the magnitudes of the current and voltages. Let's move on to part D. Show that the result of part C can be written as I is equal to V over Z, with 1 over Z equals square root of 1 over R squared plus omega C minus 1 over omega L parentheses squared. Okay, so with my observation, the magnitude of the current I sub R is capital V over R. I sub L is capital V over omega L. And I sub C amplitude is capital V omega C. So I sub L minus I sub C magnitudes will be capital V 1 over omega L minus omega C. And if I write the magnitude of the current amplitude squared to be IR squared plus IL minus IC squared, as suggested by part C, this would imply this is V squared times 1 over R squared, that is I sub R squared, plus omega C minus 1 over omega L squared and that means I can write the current amplitude as the voltage amplitude V times square root of this quantity 1 over capital R parentheses squared plus omega C minus 1 over omega L parentheses squared square root, which is V divided by Z, the impedance. So I can read the impedance of the circuit 1 over Z is equal to 1 over capital R squared plus omega C minus 1 over omega L squared, all inside the square root. That's the answer suggested by part D. Okay. So this is exactly what I have shown here. Now I want to check one limit here, which is the high frequency limit. So in the high frequency limit, what happens is 1 over omega L will go to 0, so omega C will blow up and 1 over R will be negligible compared to omega C. So this will become proportional to 1 over Z will become omega C. It's proportional to the frequency. In the low frequency limit, what happens to the impedance? 1 over Z will now approach 1 over omega L. Why? Because 1 over omega L will blow up, so this will be negligible, this will be negligible, so I will have square root of parentheses 1 over omega L squared, which is 1 over omega L. So this shows me the high frequency and low frequency behavior of the parallel RLC circuit connection. Okay, so in this example, we have looked at the parallel connection of resistor, inductor, and capacitor with parallel connection with an AC source, which has a voltage, instantaneous voltage, capital V, voltage amplitude, cosine omega t. Using the Kirchhoff current law, we see that the resistance current, inductance current, and capacitor current phasors should add up to give me the source current phasor, and their voltages should be the same. The voltages should be equal. So this requirement shows me in part B that the current phasor is in phase with the voltage phasor. For the resistor, for the inductor, the current phasor lags the voltage phasor by pi over 2. For the capacitor current leads the voltage phasor by pi over 2. So this is basically found using the relationship between current and voltage for the inductor V is equal to L di dt, and for the capacitor I is equal to C dV C dt, which is the voltage is the same for all of these three circuit elements. Now, from this phasor diagram, you can see that adding up these phasors, we get IC minus IL phasor pointing up and IR phasor pointing in the horizontal direction. This makes 90 degrees angle here. So here's my 90-degree angle. And adding these phasors as suggested by part A, IC phasor adding to IL phasor adding to IR phasor, we obtain the total current phasor. And the magnitude of the total current will be the hypotenuse of this triangle, square root of IR squared plus IC minus IL squared. And now I recognize that the current amplitude is V over R. For the resistor, for the inductor is V over omega L. For the capacitor is V omega C, because capacitive reactance is 1 over omega C, inductive reactance is omega L, and for the resistor it's resistance. So IL minus IC magnitudes will be V times 1 over omega L minus omega C. So writing this equation suggested in part C, we obtain V squared times 1 over R squared plus omega C minus 1 over omega L squared. And if we write I as V divided by the impedance, we recognize that 1 over the impedance is given by this expression. So this expression shows me that at the high frequency limit, this will go to 0. This will be negligibly small. Omega C will dominate the behavior. In the low frequency limit, this will go to 0, but 1 over omega L will blow up, so that will dominate the behavior. So the 1 over the impedance will behave as 1 over omega L. So the impedance will be like omega L. In the low frequency limit, in the high frequency limit, impedance will be like 1 over omega C. So the circuit will act like a capacitor. In the high frequency limit, it will act like an inductor in the low frequency limit.